So it's a pleasure to introduce Bernhard Hanke, who from the University of Augsburg, who will be speaking about torsion obstructions. Please.
Yeah, thank you, Marcus, for introducing me and all the organizers inviting me. So I've really spent some time during the last 2 weeks here at this wonderful place, and it's great that we're doing mathematics and having intensive discussions. So I will talk about torsion obstructions and positive scalar curvature. Apparently, this is the only talk in this workshop conference connected to scalar curvature geometry, but there is an interesting connection, especially to group homology, that I would like to point out in my talk. So we are always asked to pick up people where they are, so I start with group homology here. Just a reminder of algebraic definition, how that is defined. You can take a discrete group G, finite or infinite, and you write down free or projective resolution of Z viewed as a ZG module. And okay, so we go for homological algebra that is unique up to certain indeterminacies that disappear once we pass the homology. Of course, the homology of this complex is 0 since it's Z, but after taking the tensor product with some coefficient field f, or maybe with the integers, the complex is no longer exact. And this means we have an interesting invariant, namely its homology, that we call the group homology of G with coefficients in f. Yeah, so this is an important object for my talk. And but it's not so much about computation of this homology as we saw on the last talk, but it's more as a device for as a container for an interesting invariant. Just basic examples. So if you take the free Euclidean group on R generators, x1 up to xr, you can write down the group ring explicitly, and then you can basically write down this resolution and perform the computation, and you see this group homology in degree n with the coefficient field f is a vector space of dimension r choose n, and that happens to be the homology of the R poles, which happens to be the homology of the Euclidean space of dimension r divided by the free z to the r action. And so this connection is rather interesting, since on the left-hand side, the blue stuff is a purely algebraic construction. And on the right-hand side, we have a geometric or topological point of view. Namely, we study the so-called classifying space BG, which is e.g. any three contractible GCW complex divided by G. So you can perform this, this construction for any group G. So there are some universal constructions to do this. And then you can compute the singular homology of BG. And this may well serve as an alternative definition of group homology. And so these two definitions actually agree, which is actually quite fascinating already. And so this means that we have a connection between algebra and topology in a rather interesting manner. I will use this in order to study properties of closed, smooth, connected, oriented manifolds and their properties, especially for studying metric properties of these manifolds, or even differential geometric properties. So once you have written down M, then you can talk about, you can define its classifying map. So it's the classifying map of the universal covering of M that is determined unique up to homotopy. And then using the topological definition of group homology, you define an invariant capital phi of M with coefficients f as the image of the fundamental class of M, that's a homology class in degree n, with coefficients in f, in the M homology of B pi 1 of M, which we saw is the group homology of the fundamental group of M. So it's Hn of pi 1 of M with coefficients in M. So that's a class which is attached to any M, to any closed connected oriented smooth manifold. Of course, it may have some materiality properties, but I mean, we can just consider this class as a sort of characteristic class of our manifold of a special nature. And this class, by definition, lives in the M group homology of the fundamental group. In my talk, I will study geometric properties of M, which only depend on this class and group homology. And in the first place, it's not clear at all that there are geometric properties that may depend on this class, since, I mean, we saw an algebraic definition, we saw a topological definition, but what does it have to do with geometry? And so it's already interesting that something like this exists. I will explain this in terms of 3 examples, namely the property of being enlargeable or enlargeability of smooth manifolds. Then we have a refinement, which we call TRLF enlargeability. And in the third point, I will talk about existence and non-existence of Riemannian metrics of positive scalar curvature on smooth manifolds, and how that is related to the first 2 points, especially to group homology. Okay, let's talk about enlargeability. I have to recall a definition which was given by Gromov and Lawson in the 1980s. In their endeavor to study metrics of positive scalar curvatures and to find obstructions. So we will see this connection later. For now, I will just concentrate on this definition as it is a certain property of Riemannian manifolds. So take M as before, smooth, closed, connected, oriented manifold. And now we pick a Riemannian metric G on M. So recall this is this associates for each tangent space of the manifold an inner product, a scalar product. So we can infinitesimally measure lengths of vectors and angles between tangent vectors. And in this way, we can measure lengths of curves, volumes of domains within the manifold, and so on and so on. In particular, we have a notion of curvature, which I will recall a few slides from now. But okay, G is a Riemannian metric, and now I call MG enlargeable if the following holds. So it's an asymptotic property for any epsilon larger than 0, as small as it may be. We find a Lipschitz map, epsilon Lipschitz map. So this map shrinks everything by a factor of epsilon, f epsilon, from the universal covering of them together with its induced metric to the n sphere, round n sphere, which is of course a compact object of non-zero degree. So this picture illustrates what's going on. We have our manifold M, take the 2 pores with its induced Riemannian metric, so it's kind of, this has the shape as it is written here. Then you take the universal covering of this. This is the 2-plane. Okay, I would take actually the flat Riemannian metric on M. So there's a 2-plane and tilde, and now you can wrap around the n sphere. This 2-plane can be wrapped around the n sphere, the 2 sphere. Or in here the n sphere, and at the same time you shrink everything by a very tiny constant. So you can just, as small as epsilon may be, you find an epsilon Lipschitz map to the n sphere, which maps the blue region, which gets larger and larger when epsilon gets smaller and smaller. So this blue region is mapped to the n sphere, and all the remaining part, which is outside the blue part, is mapped to a base point. So I didn't write it explicitly, but here I mean that this map f epsilon should have this property that everything outside of a compact subset of the universal covering is mapped to one point of the n sphere. So one may call this almost proper or something like that. So we have a well-defined mapping degree, And you, for example, you can define the mapping degree by taking a regular value of this map in Sn and take its pre-image, and then count pre-image point with sign or with orientation. That's the mapping degree of epsilon. And if something like this exists for every epsilon arbitrarily small, then we call mg enlargeable. It turns out that when you have a compact manifold, as it is the case here, then this property does actually not depend on the choice of G. If you take a different Riemannian metric on M, and they are both of them are in Lipschitz correspondence with each other, and so this means you can always change the epsilon or replace it by epsilon prime and the other way around. And because this is an asymptotic property, the enlargeability condition is fulfilled either for both metrics or for none of them. And so apart from the N torus, you can also take any non-positively curved Riemannian metric G, because then the universal covering is diffeomorphic to the N plane, n-dimensional space, and so the induced metric is, so you have a map from the a metric induced by the exponential map along a point to the flat metric, which is actually on Lipschitz, and so one can compose this with the map I've written down here. So this uses the Cartan-Adamat theorem for non-positively curved manifolds. So the universal covering is diffeomorphic to Rn using the exponential map at point. And so what's the connection to group homology? This is the following thing I proved with Thomas Schick a couple of years ago. If M is enlargeable, then we study this element, which I defined before. So recall that this element is the image of the fundamental class of M under the classifying map in the nth group homology of pi1, and it turns out that this class is non-zero. So we call such manifolds Q essential. The fundamental class survives in the group homology of the fundamental group of the given manifold. And how is that proven? I can give you a proof of this fact rather quickly, since we have to think about what this actually means. What does the statement mean? Okay, you have your manifold, and you can build its classifying space, or the classifying space of the fundamental group of the manifold, by attaching cells of dimension 3, 4, and so on, that kill all the higher homotopy groups of that space, so that only the homotopy in degree 1 survives. So this is a picture or an intuition that actually leads us to a proof of the statement. Namely, what we have to prove is that if you perform the process on M, so you attach higher dimensional cells that kill homotopy groups in degree 2, 3, and so on, we have to prove that the fundamental class of M survives this process. So it's still non-trivial in this rather large space that results in the end. So the fundamental class of M does not become a boundary in this process. And why is that true? So it's just one click. So what happens if we attach the first cell to our manifold? So it's a 3-cell, say, that kills some non-trivial element in the second homotopy. Because if we attach 3 cells, 4 cells, and so on, we see a bunch of cells in the universal covering of M, which are attached to the universal cover. So the universal cover of M union D is the original universal cover of M, and we attach a bunch of cells, namely pi1M many. Okay, and we have this epsilon, but now recall that the epsilon can be chosen arbitrarily small here, and this means that if epsilon is very, very small, the boundary of one of these cells upstairs is mapped to a very tiny region of the n-sphere. And this means that this map, so this attaching map, the boundary can be extended to the whole cell. And this means that F epsilon can be extended to the blue cells that we have attached. So that's a rather simple argument, but it uses sort of metric geometry here in the, so for the first time. And that is actually the key connection between these homological computations and the metric content of such a definition. Okay, and now we do this many, many more times. And so now assume that the fundamental class of M gets killed at some point. Then this means that, okay, you take the transfer map upstairs, you have the fundamental class that becomes 0. Upstairs, you go upstairs, and then you have your map at epsilon. But we know that the image of the original fundamental class of M is non-zero to Sm. So then we have the factorization of a non-zero map through a map which maps the fundamental class of M to 0, and that's a contradiction. So such a factorization cannot exist, and this means that the fundamental class of M must survive this process or this passage to B pi 1. So that's really the only explicit proof I give during my lecture, and but that's actually a key element of all these considerations to come. And that is the key connection between this properties of group homology by attaching cells and the metric property of being enlargeable. Okay.
What's the role of the rationals in the group?
The rationals? No role. I mean, yeah.
You have a stronger theory.
So if I write Z here, it's still not zero. That's the universal coefficient theorem. Thank you for the remark. Okay, good. But we have a certain variation of this notion, which combines the enlargeability property from the previous slide with something we might call torality. So this is the following property. If you have a manifold, then you can ask, are there one-dimensional homology classes such that the cut product of these classes detects the fundamental class of the manifold? And you can ask this question, of course, also for finite field coefficients. Doesn't make any difference if F is Q or maybe a finite field with 3 or 5 elements. So that's the first thing. That's this F torality, which I defined or wrote down in the second remark. And now we combine the enlargeability property with this torality property and more or less rewrite the previous definition. And so the only thing is that this mapping degree of F epsilon from the previous slide is replaced by something we might call toral or L-toral mapping degree. So the formal definition goes as follows: for every epsilon, there is an epsilon which is mapped from some covering space of M, which I call M epsilon, can also be finite, to a sphere of a different dimension, n minus L, such that when you take the pre-image of a regular value, this is then an L-dimensional closed submanifold of M bar epsilon. So this is detected by a product of one-dimensional homology classes, C1 up to CL. So this means we take the previous definition, but we replace the usual mapping degree by an L-toral mapping degree. And we work with any coefficients here, finite or infinite. So it can be a field Q or a field with finitely many elements. So, and this makes actually difference. Yeah. So
For the company, there exists a covering or any covering.
there exists, there's also existence quantum in front of n bar epsilon.
Okay.
So there exists an epsilon which is mapped. Okay, there exists a covering and an epsilon which is just one example. And so actually now it makes a difference working with finite or infinite coefficients. So here let's take the n-torus TL cross Tn minus L, and what we can do, we can let's see, we can kill generators of the fundamental group of TL of this first factor. So we have L generators, and we kill P times each of these generators by a surgery process. So recall this means you represent generator of the fundamental of TL by an embedded sphere S1, and then you cut out a normal neighborhood of this sphere and you glue in a 2-disk cross a sphere of dimension n-1. And then this new manifold doesn't have, so the P times this generator of the fundamental will be killed in this new manifold. So this new manifold will have fundamental group, the product of the elementary abelian fundamental group of rank R, of rank L, or P, cross Z to the n-L. So it's a product of a real abelian group and of an elementary abelian group of rank L for the prime P. Okay, so this is a property here, and if you look at such a manifold, for example, if you perform this process for L equal to n, and this means you take the n torus and you kill P times of its fundamental group using the surgery process, and then you have a manifold with a finite fundamental group. Such a manifold can never be enlargeable in the previous sense, because if you have a finite fundamental group, then the universal covering is still compact, and if epsilon is too small, you will not find an epsilon contracting map to the sphere of non-zero degree. But it is still toral. It still has this property that you find elements in the first homology, in this case of the elementary abelian group for the prime P of rank L. You take the product of these classes, and this will still detect the fundamental class of n in coefficients, the field Z mod P, if we work with the prime. And okay, so one can kind of jazz up the previous proof and prove that such manifolds are still F essential. So here we have to work with field F really. If you work with the integers or even with Q, then this may no longer be true. So especially if you work with Q, this is actually false. If you take Z coefficients, then this is still non-trivial, but this element may become a P torsion element, which is killed after passing to Q. And this is kind of the reason for the type of the talk. So we have some P torsion classes in the group homology of the fundamental group that now play a role, that are just visible with finite field coefficients, but no longer with threshold coefficients. And let's think a little bit more about invariance properties of enlargeability or Tor-L enlargeability. Namely, it turns out that for any finitely presented group G, you can define a certain subset of the group homology of G with coefficients in F, which we call the Tor-LF large part of the group homology. And so in this sense, we can completely forget about manifolds and work purely in a group homological setting. How is this done? Okay, you realize EG as a simplicial complex in some way, and this can be made to a metric space by taking a standard metric on each simplex, and then you take the induced path metric on the resulting space. And now it makes sense to talk about epsilon Lipschitz maps from this space to a sphere. And it's rather straightforward to copy the previous definition to this more general context. Namely, when you take a homology class in BG, then you find a finite subcomplex of BG that carries that class. And then you can more or less write down the previous definition, taking this finite subcomplex, replacing the manifold. So you can also ask, okay, there is a certain covering of this finite subcomplex, and you have a map to the n minus L sphere. Okay, now we have to define what is the mapping degree, but that's not so difficult because you can, what you do in this context, you take the homology class downstairs, which is carried by your finite complex, and then you take the transfer of this homology class to this covering space, and the requirement is that this image of this transfer is mapped to a non-zero class of the n minus L sphere. So this is more or less the same definition. And for infinite PG, yeah, you can, as I said, you can also always take a finite subcomplex. And the most difficult part to make sense out of this definition is to prove its invariance properties. This means if you pass from a certain finite complex carrying a homology class to a larger finite complex carrying the same homology class, you must prove that if the smaller complex has this property described on the previous slide, and the larger complex again has the property. But the larger complex is attained from the previous one by attaching additional cells, and so you can actually more or less take the argument from the previous slide to prove that the property of being enlargeable or F enlargeable is invariant under passing to a larger subcomplex. So this is really a property which is attached to group homology classes of G in an invariant manner. Yeah, so in this way we kind of get rid of any manifolds or anything like that. It's just a purely metric definition of a property which is attached to group homology classes. And now it turns out that if you have a manifold, so in the end we are interested in manifolds, M, such a manifold is for enlargeable, or I mean, you can also just talk about enlargeability from 2 slides before. This is the case if and only this characteristic class I defined before lies in the subset here. So it's a complete invariant in this sense for enlargeability or enlargeability. If you are not so fond of the Tor LF part.
I have a question.
Yes.
Is there an assertion that this is non-zero or means zero?
There is the zero element is not contained in this subset.
I thought, oh, it's a linear, oh, I see.
Yes. No, but that's a very good point. It turns out that actually the complement is a linear subspace. And this implies the statement from the previous slide, because this complement, if it's a linear subspace, it always contains zero. And so zero is not contained in this subset here. So it's a little confusing, and yeah, we have to get used to it. And these large classes, so the large part of the group homology, that's not a subspace, but it's rather the small part of the group homology where all these mapping degrees have to be zero, so the small part is actually a linear subspace. And now, so the first question one might ask is, for example, yeah, is any non-zero class large in this sense? And yeah, this is the case, for example, if you take for G a 3 abelian group in n generators, Z to the n, and then you can compute this group homology. It's basically the group homology, it's basically the homology of the n torus, and then every non-zero class can be detected by a product of one-dimensional classes, and so all these classes are large in this sense. And as I explained before, it may happen that when we pass the Z coefficient, then these classes that we get here are actually torsion classes. So these were the manifolds, just remember, so we take the M torus, and we can kill L generators of this fundamental group by surgery, and we will kill the generators, but we kill P times these generators by surgery. And so we get a L total part for the prime P, and the remaining part stay as it is. At this point, one could ask, okay, is there any purely algebraic description of this large group homology? Of course, this is a very vague question, and I haven't actually thought very deeply about it. But I mean, from a kind of conceptual point of view, we saw that this group homology is defined by a purely algebraic process, writing down a resolution of G. And so, I mean, in the end, there should be some sort of characterization of those classes that share this metric property, but I don't see any direct connection between the metric considerations and the purely algebraic description of group homology. I do see a connection to the topological description using the classifying space BG and metric properties of simplicial complexes. Okay, so this is a question one might ask. Now let's pass to scalar curvature. Let's take a Riemannian manifold, and the quickest way to define the scalar curvature of this Riemannian manifold at a point P is the following. You measure the volume of an epsilon ball in your Riemannian manifold around P of radius epsilon, and divide it by the volume of an epsilon ball around 0, say in flat Euclidean space Rn. So this is a function which depends on epsilon. You can write down a scalar extension. The leading term is 1, and the next term is of order 2 in epsilon. And this actually defines the scalar curvature up to a coefficient minus 1 over 6n plus 2, which is just a convention. And then we have higher order terms. So the scalar curvature measures the asymptotic volume growth of balls in Riemannian manifolds for radii tending to 0. And so there is an important distinction to Ricci curvature, which is a more complicated invariant, a finite invariant, and this actually measures volumes of macroscopic balls, whereas the scalar curvature measures the volume of infinitesimally small balls. So that's here the main distinction. And okay, when you look at the n sphere and you take such a ball around the north pole P, then its volume is a little smaller than the Euclidean volume, and this means in the scalar extension, the scalar curvature must be positive. So observe the minus sign in front of the second term. So the scalar curvature is positive in this case. If we take flat Euclidean space, then of course it's 0. All the terms of order higher than 0 disappear, and in hyperbolic space, the scalar curvature becomes negative because this ball has a larger volume. And I mean, this is a very, studying manifolds with certain scalar curvature properties is a very rich subject, which I find very interesting. And I can just indicate a few facts which make this field interesting. So, okay, so the first thing is, of course, we have an analytic definition, which we learn in courses about Riemannian geometry using the Riemannian curvature tensor. In dimension 2, the scalar curvature is basically the Gauss curvature. It's 2 times the Gauss curvature from elementary geometry of surfaces in a 3-dimensional space. And there is a connection of scalar curvature properties to general relativity, namely the scalar curvature non-negative is related to what physicists call the dominant energy condition, at least for totally geodesic submanifolds of semi-Riemannian manifolds. So you can then write down dominant energy condition, and this translates to the property of the scalar curvature of such totally geodesic submanifolds. And if they are not totally geodesic, then one can write down a more complicated expression. But there is an important connection of scalar curvature geometry to general relativity, and there are also interesting connections within mathematics. Scalar curvature has connections to many fields, and I will point out some of them on one of the next slides. Maybe we study the scalar curvature just to begin with in dimension 2. So this is just a reminder. All of you probably know what's going on here. So we have the Gauss-Bonnet formula, and we have a connection between the Gauss curvature, which is the scalar curvature in dimension 2, with topological properties. So if you have a finite polyhedron X, write down its Euler characteristic, it's a finite number, which is equal to either 0 or 2. for the n sphere, depending on the parity of n, then the order characteristic of the n torus is 0, or of the n ball is 1. And okay, so if you have a complicated object, then you can write down a triangulation with tiny triangles, you have to count a lot, but in the end, if you take this sum with changing signs, then you get always 0, independent of what triangulation you take. Okay, and so this homological invariant chi of n can be computed using the scalar curvature. And for example, this already implies that if you have a torus T2, or if you take this surface of genus 3, we know that this has negative Euler characteristic, and so this already implies that there is no metric G on this manifold which has everywhere positive scalar curvature, which is everywhere positively curved. And you see this already in this picture here, that there are some points which are non-positively curved, which have a more hyperbolic shape. Okay, so this is in dimension 2. In dimension 3 and higher, the picture becomes a little bit more diverse. The diversity is always important, even in mathematics. So in dimension 3, we have a pretty good understanding which manifolds admit Riemannian metrics of positive scalar curvature, though this I really by existence of PSC metrics. But in higher dimensions, so the picture is a little bit more complicated. So we have several sources of obstructions here, and actually, so these sources are somewhat different. One world that is connected to scalar curvature geometry is spin geometry, and the spectral geometry of the Dirac operator. So this is quite interesting because we have a close connection to the Atiyah-Singer index theorem. And then another source of obstructions against the existence of positive scalar curvature metrics is largeness, which I defined. So I mean, certain instances of this property were defined before using enlargeability. And in fact, it can be proven that if you have a spin manifold which is enlargeable, then such a manifold does not admit a positive scalar curvature metric like the n tori. This is a result of Gromov and Lawson. And yeah, so largeness is even so for smaller dimensions up to 7 or maybe a little higher. The largeness is also an obstruction without assuming the spin property. Okay, so here in the middle we have the so-called Gromov-Lawson-Rosenberg conjecture, which has a lot to do with K-theory of group rings and the completions of those, so K-theory of C-star algebras, things like that. And then on the right-hand side, we have these largeness properties. The first is enlargeability, which I defined on the first slide, or the second slide. And then we have this torality property. So remember, this means that products of one-dimensional classes detect the fundamental class with some field positions, and the intersection of these two fields, of these red bubbles, is this enlargeability that I defined before. Yeah, then we have some sporadic obstructions. One comes from cyber-fitting theory in dimension 4, the other one from harmonic maps in dimension 3. So it's rather interesting and really, it's a very rich subject which has interconnections to many fields in geometry and topology. And actually, there is also quite a remarkable connection to algebraic and geometric topology, even to Cobotzen categories. So even so, the newest or rather new developments in topology are connected to scalar curvature geometry. And okay, so what does this have to do with TOR-LF enlargeability? Yeah, so this TOR-LF enlargeability is an obstruction. So here I have a certain dimension restriction of our manifold M. I assume that its dimension is at most 7. This can be weakened, but we do not know if it's how it works in all dimensions, since we use a certain analytic tool, namely the generalized minimal height surfaces, mu-bouts, and there are certain regularity issues of those objects which make it difficult to prove such a statement in higher dimensions. But at least in dimension up to 7, we can write down the following theorem. Namely, we look at TRHW02 enlargeable manifolds. And remember, this depends on such a this given field F. It can have characteristic zeros and fields with, so for example, you can take the rationals here, or you take fields of finite characteristics, Z mod 2 or Z mod P for P larger than 2. And depending on these characteristics of F, we get the obstruction to the scalar curvature metric on such a manifold. For example, if you have for LF enlargeability for the rationals, then you always get an obstruction up to the dimension of n, so L can be anything. And if the characteristic of F is equal to 2, then we have to assume that L, so this total part, represents the total part of the manifold is has dimension or rank at most 2, and if the characteristic is larger than 2, then this total part can have dimension up to 3, and so then we get this existence, we get a non-existent statement of positive scalar curvature matrix. So then we find some homological obstruction phenomena Schick in the 90s of the last century. And let me say a few words about the use of new bubbles, since it is not clear at this point how we get an obstruction to positive scalar curvature at all. I can just indicate what's going on. And maybe I do this with a classical example, namely the N torus. So take a torus, N torus S1 cross S1 cross S1, say up to dimension 7, and assume that this has a metric of positive scalar curvature. And what one can do is the following: take a homology class, which is dual to a non-zero class of degree 1. So you take a homology class which is represented by a hypersurface in this torus. And now, by geometric measure theory, one knows that you can actually represent this homology class by a hypersurface which is minimal in the sense of Riemannian geometry. So it's a mean curvature vanishes, and it's actually stably minimal. So small perturbations do not decrease surface areas in small regions. Okay, so let's take such a minimal hypersurface which represents the dual, or which represents a non-trivial homology class of dimension n-1 in this torus. And now computation shows that this hypersurface, which has one dimension less, again admits a positive scalar curvature metric. And now what you can do, induction, going down one step at each time, and in the end you arrive at a manifold of dimension 1, which is S1, and this does not admit a metric of positive scalar curvature, and then you have a contradiction. So this is roughly the way this is proven, and you see already at this point that it's good to have one-dimensional homology classes in order to perform this construction, and therefore the torality property is very helpful here. It's not so clear how we use the enlargeability property for such a proof, but one can apply a trick to kind of translate this condition into a torality condition, and then basically the same proof works. And this assumption that M is most heavy can be weakened, as I said before. Now we can be sure that it works up to dimension 10, but in higher dimensions we have these regularity issues with the new bubble technique. But here at least we have this property of, so we have these obstructions, and now we can ask which of these assumptions are really necessary to write down such a statement, and we can at least have partial information on that. Namely, okay, so if you have a characteristic of f equal to 0, think of the rational field, then there is no PSC metric on our manifold independent of the choice of L, so this total part. But if the characteristic is 2, then starting from L equals 3 or L equals 4, we do get positive scalar curvature metrics. This is rather interesting. So it really depends on the characteristic of our field here. And if the characteristic is larger than 2, we know from the previous slide that for L equal to 2 or 3, so the total part has dimension 2 or 3, we do not have positive scalar curvature matrix, but for L at least 4, it's the question is actually open. So I can maybe illustrate this by elementary picking up on the previous slide. Take, say, a 5 torus T5 and kill 3 times each generator of its fundamental group by surgery. Then you have a manifold whose fundamental group is equal to elementary abelian 3 group of rank n or rank 5, because we started with a 5 torus. It's not known to us whether this manifold emits positive scalar curvature metric or not. So that's an open question, and this is a little annoying actually, because we have so well-developed tools in the field to study the existence of positive scalar curvature metrics, but even in this rather elementary example, it's unknown if such a manifold emits a PSC metric or not. And yeah, one might speculate that one can replace this technique I mentioned before with taking minimal hypersurfaces representing duals of integral cohomology classes in degree 1 by something that reflects the mod P nature of this question here. But the problem is if we work with this manifold, which I described before, then the integral first homology is actually 0. You only see elements after passing to the field Z mod 3, in this case, using the universal coefficient theorem. And this means there is no interesting hypersurface of codimension 1 unless we pass to a more general class, which people call mod P minimal hypersurfaces. They represent mod P homology classes of codimension 1, but it's not clear how this connects to the positive scalar curvature property. And this is really a wide open question. That's rather interesting. And so now let us come back to properties of geometric properties of smooth manifolds that are completely characterized by the image of the fundamental class of M under the classifying map. And interestingly, the existence of positive scalar curvature metrics is one of these properties. So it's not just enlargeability or TRLF enlargeability, which may appear a little artificial, but actually the existence of positive scalar curvature metrics is controlled alone by this class alone, at least if the universal covering of M is not spin. So this means we are not in the left bubble we saw on the previous slide. So if M tilde is not spin, then the only obstruction of being PSC or admitting a PSC metric lies in this element, or we can reformulate it in dimension at least 5 for closed-oriented manifolds whose universal covering is not spin. The property of admitting a positive scalar curvature metric only depends on the image of this class. So that's the class large or capital phi I defined before. But here I have to take integral coefficients. It does not work with field coefficients. We really have to work with integral coefficients here. And I mean, proving such a statement involves a whole bunch of techniques, which most of which were actually developed in the 80s and 90s. And I can just roughly indicate how one proves such a statement. A key point is the property we call Bordism invariance of admitting positive scalar curvature metrics. This means if you have one manifold which is bordered, maybe oriented bordered to another manifold which admits a positive scalar curvature metric, then the original metric also admits a positive scalar curvature metric under certain additional conditions. So certain inclusions into the border have to be highly connected. But roughly that's the picture. So if you think of Bordism theory, this has a close connection to scalar curvature geometry using this principle. And this principle is in the end proved by a surgery invariance for positive scalar curvature metrics. Namely, if you have a manifold that is equipped with a Riemannian metric of positive scalar curvature and you apply a surgery to this manifold of 4 dimension, at least 3, the new manifold again has positive scalar curvature. And now observe that when you have a Bordism, then you can subdivide this into a step of surgeries using Morse theory. And so we have a close relation between these two principles here. So that's a key point. So the existence of positive scalar curvature methods is in the end governed by Bordism theory. In this case, we can use oriented Bordism. And now the problem is how do we pass from Bordism to homology? And of course, when you take the Bordism or oriented Bordism of B pi 1 and map it to homology, then you lose a lot of information. And you have to prove that everything which is in the kernel of this map, which disappears in the group homology, does not destroy your picture. So all those elements have to admit positive scalar curvature metrics. So they must be positive Bordism classes. They must have a representative, which is PSC. And so this means one has to study the map from MSO, from the Bordism spectrum to the Eilenberg plane spectrum, and study elements which lie in the kernel when you apply these homology theories to the states in pi 1. And this has to do with using stable homotopy theory. This was then greatly developed by Stefan Stolz in the 90s and before by Gromov and Lawson in the non-spin case. So we have to use this property, and there is another feature that when you also, I think you subdivide this problem into several pieces. One is the prime 2, and one is the primes larger than 2. And for the primes larger than 2, you have also you need to study positive scalar curvature metrics on manifolds with certain singularities, with vast Haldane singularities. So this, but in the end, one has such an invariant statement, and so this is another property which only depends on this characteristic class. And now one can ask again, take some group G and take its homology with integer coefficients, which of these classes admit positive scalar curvature metrics? So which classes can be realized as images of fundamental classes of positive scalar curvature metrics under the classifying map? And what we know is that these positive classes cannot be enlargeable or TORLF enlargeable in certain degrees. This is what we saw in the previous slide. So we have an interconnection, a relation between all these different properties. And now we apply both aspects of what we learned, namely the obstruction property and the existence property of positive scalar curvature metrics measured in terms of group homology to construct a funny example of the following kind. Namely, let's take two manifolds M1 and M2, whose product has dimension at least 5. I also assume that M1 tilde, so the universal covering of M1 is not spin. This means the second Stiefel-Whitney class does not vanish. And now assume, okay, we take these two characteristic classes, we take the image of the fundamental class of M1 under the classifying map in the group homology of pi 1 and 1, and we take the fundamental class of M2 under the classifying map in the group homology of pi 1 of M2 with integral coefficients. And we assume that these two classes are torsion classes in their respective homology groups of O prime O. And then I claim that M1 cross M2 admits a positive scalar curvature metric. Why is that? The proof is half a line, namely, if you take the image of the fundamental class of M1 cross M2 in the group homology of M1 of the fundamental group of M1 cross M2 with integral coefficients, this is 0. Why is that? Yeah, it factors through the individual group homologies, and then you apply the unit formula for computing the group homology of a product. And because these two classes have full prime order, when you take the tensor product of these two group homologies, and this tensor product, the tensor product of the individual classes is 0. And so this class is 0 here. This is very easy, and the 0 class in group homology is always of positive scalar curvature, because, I mean, what you can do, you can just map a sphere of the respective dimension. You can just take such a manifold which admits positive scalar curvature, take a map to B pi 1 of M1 cross M2, and take the image of the fundamental class, and this has positive scalar curvature, of course. So, so the class 0 is positive, and therefore this manifold M1 cross M2 admits a positive scalar curvature metric using the theorem of the previous slide. And now let's take a concrete example. And this comes back to these manifolds I constructed before. What we can just play around. So take a 7 force T7, and then take the prime 13, say, and kill 13 times generator of the fundamental group of T7. So we have generators which generate factors of Z. We kill 13 times these generators for 3 elements. So the fundamental group of the resultant manifold is an elementary abelian group for the prime 13 of rank 3. And to make it non-spin, or the universal covering non-spin, I just take the connected sum with CP2 cross S3, which is simply connected and not spin, and it has the right dimension, namely dimension 4 plus 3, so dimension 7. So, and this manifold doesn't admit a positive scalar curvature metric because we have the obstruction from the previous slide. And the same thing applies to the manifold taking the prime 17, and we kill 3 times 3 generators, or 17 times 3 generators of the fundamental group of the 7 torus, and this manifold doesn't have positive scalar curvature metric. And we saw before that these classes which appear here, they actually are both torsion classes. One class is 13 torsion, and the other one is 17 torsion. So they are of 4 prime order, and therefore the product of these two manifolds admits a positive scalar curvature metric. So you have 2 manifolds, each of which is large in a certain sense, namely in the sense of torality enlargeability, and therefore they do not admit positive scalar curvature metrics, but the product does. And in this sense, the product is small. So when you think of manifolds being positively curved as small manifolds, I mean, this intuition is not entirely correct, as this example showed, but this is our natural intuition that we have. I mean, there are also other sources of such examples that were known before. So it was known before that it's possible to have 2 manifolds not admitting positive scalar curvature metrics, but their product does. But this is a new class of examples that is rather elementary, since it just uses torsion properties of group homology classes. So there is no complicated spin geometry involved or anything. So this means this is kind of the slope, and the products of large manifolds can be small. So we apply we combine these 2 aspects, the obstruction aspect and the construction or existence aspect, to obtain such examples. Okay, so on the last slide, I just have a bunch of papers of bibliography on which my talk today was based. So these largeness properties for group homology, so we investigated them together with Michael Brunbauer some 14 years ago in the Journal of Topology, large and small group homology, and then scalar curvature geometry. As I said before, it's a rich field. There is a very comprehensive article written by Gromov in Perspectives in Scalar Curvature volume. And so the title of this paper is 4 Lectures on Scalar Curvature. It has 514 pages, so it's a very rich source of theory of open questions, and in particular of very interesting ideas how one can proceed in this field. So this is a treasure box. And I think that we will be dealing with questions asked in this paper for many, many years and coming decades. And so this particular aspect of having total obstructions to positive scalar curvature is a paper that appeared in the first version in 21 and was revised last year in 23 on the article. Yeah, so I thank you for your attention. And
Yeah, thanks, Bernhard, for this really nice talk. Question for the speaker.
The manifold is essential, it does not agree.
very good question. I wasn't sure if I should write down this conjecture. This is, but now that's an occasion to say or speak it out. Namely, if you have a closed-oriented manifold, which is essential, Q essential, the conjecture says it does not omit a metric of positive scalar curvature.
So your very first theorems were just one direction, right?
Yes, exactly. And now let's think about this conjecture a little bit. Because some people insisted on Q versus Z or something like that. If you take RP3, then it's, I mean, the fundamental class of the manifold is mapped to a non-zero class in its group homology with Z coefficients. But it's a two-torsion class. So this means this manifold is essential. We see this Z essential, but it doesn't admit a metric of positive scalar curvature. So the case of prime 2 is always very special. This makes it at some places. So let's rather talk about Q coefficients, but then it's a kind of a fundamental open question. If you have a Q essential manifold where this characteristic class is non-zero with Q coefficients, the conjecture says such a manifold does never admit a positive scalar curvature metric. A special case of this conjecture, which is also unsolved, is that spherical manifolds do not admit metrics of positive scalar curvature. So manifolds whose universal covering is contracted.
That was my first question, which I was afraid to ask.
Yeah, that's and that I mean it's known in dimension up to 5 now. Okay, so for long while it was known up to dimension 3, and then in dimension 4 and 5 there were breakthroughs by Torsion and Lee on the one hand, and Michel Gromov during last year. So up to dimension 5, we know that this conjecture is true, but in higher dimensions it's completely open.
Okay, I have another question.
Yes.
With a candidate for conjecture. So take a symplectic manifold, the symplectic for subprimes in K by 1 to homology, or comes from K to 1. So in particular, it's essential.
Is it? Okay.
Because the whole form.
In the group homology?
I think the one to homology.
Okay.
Symplectic form comes from
Yes.
from the group. So can you say something about such manifolds, which are essential?
Okay, we haven't looked at this, I have to admit. I mean, symplectic manifolds take.
I'm asking this question because, in symplectic work, you might have something coming from Soviet within your.
Yes.
If you're very much.
That is very true, but I do not have a good answer right now. Maybe we discuss this later after the talk. Yeah.
Yeah, so all these terms are about existence or non-existence of metrics. In the cases where they exist, what can you say about the sort of space of all such metrics? There's some kind of interesting monolith space.
Yes. That's another rather large subject within the field of positive scalar curvature geometry. We do have a lot of knowledge about the space, especially higher order groups of these spaces, namely of the space of positive scalar curvature metrics and of moduli spaces of positive scalar curvature metrics on large classes of manifolds, including spheres. And we nowadays know that in most cases, all these homological groups are not trivial. Right? But this uses always a spin geometric technique. So the world that was on the left-hand side, the gray bubble, the gray cloud. But this has extremely interesting connections to advanced methods in in geometric topology, like pseudo-isotopic theory, algebraic theory, and as I mentioned before, the Wilson category. So a very important result is due to Hoffini, Ebert, and Randall Williams using Wilson categories, and they proved so they proved the result on the space of triviality result on higher monotopic groups of space of positive scalar curvature metrics using topological properties of proposal categories. And of course, in the end, the connection comes via the surgery theorem and Wilson theorem. And yeah, we also have some knowledge about the moduli spaces. I worked on that with Mark Walsh, who's revealing the too much Schick of 2010, and we proved non-triviality of the spaces. But there are other works as well that I didn't mention now. It's a rich and active subject.
So now knowing those moduli spaces, can you construct examples of positive curvature metrics on total spaces and bundles?
On what?
On total spaces and bundles.
Yeah, we saw this in the G2 talk last week, and that principle underlies the construction of non-trivial classes in moduli spaces of such metric. Because as I mentioned before, you have this Bordison principle for constructing positive scalar curvature metrics, and this can also be applied to vibration. If you have a vibration, even if you have a non-trivial vibration. Yeah, this plays an important role.
Further questions for Bernhard?
Do you have any idea how to realize these not P minimalist bases that you look into that direction?
That pure speculation I have to. I mean, the problem is I'm not very familiar with the analytic subtleties in geometric measure theory, but I do know that people talk about not minimal hypersurfaces. And so I'm sort of optimistic that one day we will find a connection. But it's really not clear at all. Maybe it's just a dream. Since, as I mentioned, if you have a smooth minimal hypersurface, then you have positive scalar curvature using a second variation formula. And but in this more P world, it's not clear at all if something like this does work in any sense. So maybe sometime in the future we will know how this works. But and maybe it's wrong. Maybe these things do happen on negative positive scalar curvature that we just haven't found. That's very well possible. But the conjecture is that they do not admit. And actually, this is sort of funny. In our first version of the article, we phrased it as a question, but then Bishop Gromov said, no, let's write down a conjecture, because this is a better motivation for people to work on this, so then you can find an account of the conjecture, or you can prove it. Both things are maybe more exciting than answering the question. That's the psychology of mathematical research. Sociology.
Let's thank Bernhard again.